Under the glow of emergency lights, the control room at NASA suddenly flashed red. An alert unlike any other had just triggered. The system designed to track celestial hazards didn't just ping a random rock, it flagged an object on a deadly intercept course. That object is 3I/Atlas, an interstellar now hurtling toward Earth's moon. Observations confirm an extreme scenario. NASA has declared a Level 2 emergency, the kind of designation reserved for threats that might actually collide with a celestial body. Sources tracking asteroids show similar alerts happen only when odds, however small, shift toward real danger. At this moment, scientists face a chilling question. If 3I/Atlas impacts the moon, what happens next to the lunar surface, to our orbiting satellites, even to us on Earth? Everything we thought fixed and safe suddenly feels fragile. Because in that instant, humanity's greatest fear is no longer about distant stars. It's about the silent thing accelerating right toward our satellite. NASA's early data confirmed it. The object had a name, 3I/Atlas, the third interstellar visitor ever recorded in human history, following Oumuamua in 2017 and 2I/Borisov in 2019. But unlike those harmless passers-by, this one wasn't drifting away. It was diving straight into the moon's gravitational field. Tracking sensors calculated its speed at over 150,000 miles per hour, fast enough to cross the distance from Earth to the moon in just a few hours. Within minutes, NASA's impact simulations were running non-stop, each scenario more alarming than the last. The results showed a potential crater between 12 and 18 miles wide, an explosion powerful enough to be visible from Earth's night sky with the naked eye. In Washington, the Planetary Defense Coordination Office declared a full emergency posture. Coordination lines opened between NASA, the European Space Agency, ESA, and Japan's JAXA, establishing a synchronized 24-hour watch. Every shift of trajectory, every fluctuation in light intensity was logged in real time. The possibility that humanity might soon witness the first-ever collision between an interstellar object and Earth's natural satellite turned what was once an academic curiosity into a global obsession. At Harvard, astrophysicist Avi Loeb, whose earlier research on interstellar objects like Oumuamua challenged traditional explanations, began examining 3I/Atlas with cautious interest. His team compared its motion to previous anomalies, noting that its precision and stability resembled the kind of control no natural comet should possess. Loeb didn't make public claims about its origin, but his past work had already raised the possibility that some interstellar travelers might not be entirely natural. Meanwhile, inside NASA's Jet Propulsion Laboratory, scientists faced a haunting paradox. The object's path seemed unaffected by solar wind or radiation pressure, behaving as if something was guiding it. As days passed, debates intensified between two camps: those who saw a once-in-a-lifetime opportunity for study, and those who saw the prelude to a planetary-scale disaster. If the moon were struck, tidal models predicted minor but measurable disruptions in Earth's rotational stability, altering tides and orbital resonance. It wouldn't destroy the moon, but it could shake the delicate balance that has shaped life for billions of years. As telescopes across the world locked onto the fast-approaching glow, a strange calm settled over mission control. There was nothing to launch, nothing to stop. All anyone could do was watch and count the seconds. The countdown had begun, not to prevent impact, but to witness what the universe was about to do next. As new readings poured into NASA's control systems, the numbers began to twist into a shape no one wanted to see. The once distant interstellar traveler, known as 3I/Atlas, was no longer on a clean, predictable arc. It was slowly bending south, its trajectory curving toward the moon's lower hemisphere. At first, the deviation seemed minimal, a margin of error well within expectations. But every new update narrowed that margin, revealing a silent drift that was anything but random. The simulations were merciless. Even a deviation of less than 1 degree could pull 3I/Atlas into what mission specialists called the window of gravity, a razor-thin zone where the moon's gravitational pull could overpower solar influence and send the object plunging downward. Inside that corridor, escape becomes almost impossible. At its current velocity of over 150,000 miles per hour, impact could happen in under 3 weeks if the drift continued. At the Goddard Space Flight Center, engineers ran thousands of Monte Carlo simulations, layering variable after variable. Each run came back with a smaller chance of a miss. It's like watching a slow collision in real time. One mission analyst whispered during a press briefing, "Observatories in Hawaii, Chile, and the Canary Islands confirm the shift." 3I/Atlas's light now tracked directly toward the moon's south pole, specifically near the Shackleton crater, a region scientists have long studied for frozen water deposits. If a collision occurred there, models predicted a plume of lunar dust rising hundreds of miles high, potentially altering the moon's brightness and color for months. Meanwhile, the team at Harvard, led by Avi Loeb, kept revisiting a troubling question. Why did 3I/Atlas's orientation remain so steady? Normal comets spin and tumble chaotically, but this one held its posture, adjusting in subtle bursts that seemed rhythmic. The European Space Agency's solar orbiter picked up faint gas emissions that appeared synchronized with these course changes. Short, evenly spaced, symmetrical, not random. Inside NASA's Jet Propulsion Laboratory, the debate was reaching a fever pitch. Some argued the movements were the result of natural outgassing. Others pointed to the timing, the precision, and the fact that every course correction aligned perfectly with gravitational windows. The data didn't just show a comet reacting to physics, it looked as though it was responding to something. By week's end, the impact corridor had shrunk to less than 200 miles across the lunar South Pole, the narrowest uncertainty zone ever recorded for any interstellar object. One engineer's comment summed up the unease better than any official report. If it drifts another degree, we'll witness the first interstellar impact in history. And as the countdown clock on the mission dashboard ticked down, a single question began to haunt every scientist watching the data feed. Was this just the pull of gravity, or the first sign that we're not alone in guiding it? At NASA's Goddard Space Flight Center, the numbers painted a scenario that looked more like science fiction than reality. If 3I/Atlas struck the moon, the resulting blast would unleash an energy equivalent to several hundred megatons of TNT, more than 10 times the yield of the Tsar Bomba, the largest nuclear device ever detonated on Earth. Unlike Earth, the moon has no atmosphere to absorb or disperse the shock. Every ounce of that force would drive straight into its surface, sending seismic waves rippling through the lunar crust and echoing deep into its core. The simulations showed a crater nearly 20 miles across, carved out in an instant. The impact would hurl billions of tons of lunar dust and debris into space, forming a halo of glowing fragments orbiting the moon like a second, smaller satellite. For hours, maybe even days, the moon's entire outline would shimmer with an eerie, silver-white radiance, bright enough to be seen by the naked eye from every continent on Earth. For the first time in human history, people could stand under the night sky and witness a celestial explosion with their own eyes. News networks prepared live broadcasts, while observatories scrambled to recalibrate their telescopes to capture the flash. Astronomers predicted the light from the impact would be visible even during daylight hours, rivaling the brightness of Venus and reflecting off the upper layers of Earth's atmosphere like a ghostly mirror. But behind the awe, the warnings were serious. NASA's Planetary Defense Coordination Office published a statement cautioning that the same dust cloud creating that breathtaking glow could also disrupt the moon's reflectivity, its albedo, for months or even years. The moon acts like a stabilizing anchor for Earth's rotation and tides. Altering its surface properties even slightly could change how sunlight and gravity interact with our planet. Oceanographers warned that shifts in tidal amplitude might follow, causing stronger coastal surges and irregular sea patterns. Climate scientists added that long-term dimming of moonlight could subtly affect nocturnal ecosystems, animal migrations, and atmospheric rhythms that have remained constant for millennia. Still, the human fascination was unstoppable. Social media lit up with the phrase "second moon" as millions imagined what the night sky might look like when the explosion finally came. Artists rendered digital visuals of a glowing lunar halo stretching across the heavens. The beauty of it all almost made people forget the danger it represented. Back in Pasadena, engineers monitoring the high-speed impact models could only stare at the growing probability curve on their screens. One scientist broke the silence in the control room. "When it happens, the light will reach us in 1.3 seconds. By then, it'll already be over." It was a sobering reminder that humanity, for all its technology, could only watch. The cosmos wasn't asking for permission, it was acting on its own scale, in its own time. As the countdown edged closer to zero, a quiet realization spread across every observatory on Earth. For the first time, we would see the universe move, not as something distant or abstract, but as something alive, capable of shaking both the heavens and the fragile world beneath our feet. The closer the potential impact drew, the more scientists began to realize that the real danger might not be what they could see, but what they couldn't. NASA's seismologists ran complex resonance models and found something unnerving. If 3I/Atlas struck the moon, the resulting seismic shockwaves could make it vibrate for hours, producing what they called the lunar bell effect. That term wasn't poetic, it was literal. In 1969, when Apollo 12's spent rocket stage crashed into the moon, seismometers recorded vibrations that lasted nearly an hour, as if the moon had rung like a bell. The data from that experiment changed how humanity understood the moon's interior. Now, scientists feared they might hear that sound again, but this time on a scale thousands of times stronger. NASA's network of retrofitted Apollo seismic stations, still partially functional thanks to modern telemetry relays, would instantly become priceless. Every tremor, every echo moving through the lunar crust could reveal what no probe or radar scan ever had: the composition of the moon's deep core. For planetary scientists, it would be a once-in-a-lifetime opportunity, a direct glimpse into a world that has remained silent for 4 billion years. But beneath the excitement ran an undercurrent of fear. If the impact occurred on the near side, the hemisphere facing Earth, some researchers warned that the gravitational coupling between the two bodies could allow faint seismic feedback to resonate back toward Earth. While the energy would be weak, even minor fluctuations in the moon's mass distribution could slightly alter our planet's rotation and tidal cycles. The idea sounded dramatic, but NASA's Goddard Institute for Space Studies confirmed that such a chain reaction was theoretically possible. Over long timescales, these shifts could nudge ocean tides, subtly adjust the length of a day, or disrupt the orbital synchronization that keeps Earth's axis steady. Even the smallest change in the Moon's behavior, one NASA official explained, can ripple through everything. From the timing of our tides to the migration patterns of marine life. Around the world, climate researchers began calculating what those changes might mean. A tenth of a degree alteration in Earth's tilt could affect seasonal rainfall. A few seconds added to the length of a day might influence atmospheric currents. The Moon's calm, constant pull, the silent metronome of life, could suddenly falter. Inside mission control, silence replaced speculation. The question was no longer how much damage the Moon could take, but how much Earth could endure if its only natural satellite was thrown out of balance. As one geophysicist wrote in a late-night report, "We've spent centuries studying the Moon's light. Now, for the first time, we might feel its heartbeat, and it could change the rhythm of our own." The approach of 3I/Atlas forced NASA and every major space agency on Earth to confront an uncomfortable truth. Humanity's planetary defense system had a blind spot large enough to fit an entire world through. The Atlas network, designed to scan for asteroids within our solar system, had detected the object only after it had already crossed the boundary of our cosmic neighborhood. By the time the alert went out, it was already inside the inner solar system. Too late for any intervention. In the days that followed, internal reports leaked from NASA's Planetary Defense Coordination Office, revealing what many scientists already feared. The entire detection framework was built around predictable orbits, not interstellar visitors moving at hyperbolic speeds. In other words, 3I/Atlas had slipped through a gap in human awareness, a flaw no one had imagined until it was too late. As headlines erupted around the world, the blame game began. Congressional hearings demanded explanations. The European Space Agency argued that responsibility should not rest on one nation. Japan's JAXA called for a global early warning alliance, while China's CNSA quietly expanded its own sky survey program. Yet none of these measures could change one simple fact: the countdown to a potential impact was still ticking. In Geneva, during an emergency session of the United Nations Committee on the Peaceful Uses of Outer Space, a delegate from Brazil posed a question that echoed in every newsroom. If the target wasn't the Moon, if it was Earth, would we have known in time? The silence that followed said more than any statement could. NASA's simulation team ran contingency models, calculating what might have happened if 3I/Atlas's trajectory had deviated by even 1% toward our planet. The result was chilling. The impact energy would equal 10,000 nuclear bombs, releasing enough heat to ignite the upper atmosphere and send debris clouds circling the globe. Within days, sunlight would dim, temperatures would plunge, and global weather patterns would collapse into chaos. Planetary scientists compared the projection to the Chicxulub event that wiped out the dinosaurs. The difference was simple. This time, humanity would have seen it coming, but still could have done nothing to stop it. In the following days, across scientific circles, the message was clear. 3I/Atlas was not just a cosmic anomaly, it was a reminder of how fragile our awareness of the universe still is. They emphasized that current detection systems were never designed for fast-moving interstellar bodies and confirmed that plans were being discussed for a new generation of wide-field trackers capable of scanning beyond the heliopause. According to NASA's preliminary roadmap, such systems would take years to develop and deploy. leaving Earth temporarily dependent on existing early warning networks. For now, all anyone could do was watch the data scroll across the monitors and listen to the ticking of a clock counting down toward the unknown. As one scientist summarized grimly, "We're learning our hardest lesson the only way we can, by watching it unfold in silence." As 3I/Atlas closed in, the world split into two camps: those who saw it as science's greatest opportunity and those who saw it as the beginning of a cosmic disaster. Across observatories from Hawaii to Chile, telescopes operated non-stop, feeding terabytes of data into global servers. Every flicker of light, every spectral reading was cataloged in the hope that one day it might explain how an interstellar traveler behaves at the moment of impact. Within NASA, the divide was growing. One faction, composed mostly of astrophysicists, argued that this was the first chance in human history to observe a real planetary-scale collision, something no simulation could ever reproduce. "We've modeled these events for decades," one researcher told Nature, "but never witnessed one. This could rewrite our understanding of impact physics." The other side, led by engineers and planetary defense experts, warned that treating it as an experiment ignored the stakes. Their projections showed that even a glancing blow could destabilize the Moon's orbit or trigger dust storms capable of dimming Earth's sunlight. "We're playing scientist while standing under the hammer," said one senior NASA analyst during a heated internal meeting. Amid the tension, the private sector entered the race. Companies like SpaceX and Blue Origin received direct requests from NASA and the European Space Agency to prepare robotic probes capable of reaching the Moon's south pole. The goal wasn't intervention, it was observation. The probes would land before the predicted impact, recording data from the ground that satellites couldn't capture. But even these missions faced moral and logistical questions. What if the very act of launching interfered with the debris trajectory? What if they arrived too late? Public opinion fractured along the same lines. On social media, the question spread like wildfire. Should humanity try to destroy the object or let it fall and learn from the consequences? Some argued for using nuclear propulsion systems to alter its path, invoking the same technologies tested under NASA's DART program. Others, including many in the scientific community, insisted that interfering might erase the most valuable natural experiment in history. Religious and philosophical voices soon joined the debate. Clergy members called the event a divine test, while skeptics dismissed it as coincidence. The story of 3I/Atlas began to transcend science, becoming a mirror for human belief itself. In one televised roundtable, a planetary scientist summarized the dilemma in a single sentence. "This is the universe running its own experiment, and we, for once, are both the spectators and the subjects." As the object drew nearer and its green light shimmered across lunar orbit, the world held its breath. Some prayed, others calibrated instruments, and a quiet truth began to take hold: that to truly understand the cosmos, humanity might have to watch it destroy what it loves most. In the final week before the predicted impact, something strange began to happen. NASA, once eager to share every update, fell silent. The agency's official website, which had been streaming live trajectory data for weeks, suddenly froze at a data integrity review. Press briefings were postponed without explanation. For a world that had been watching every heartbeat of 3I/Atlas, the silence was deafening. Independent astronomers tried to fill the gap, comparing their own readings with archived NASA data. That's when the first irregularities surfaced. Telescopes in Arizona and the Canary Islands recorded unusual fluctuations in brightness near the Moon's southern limb. Pulses that didn't match any known pattern of natural comet behavior. Instead of a steady approach, 3I/Atlas seemed to be slowing down, then accelerating again in rhythmic intervals. Inside NASA's Jet Propulsion Laboratory, insiders described growing unease. One anonymous engineer, quoted in a report by the Washington Post, claimed that the data showed energy spikes inconsistent with gravitational influence. In other words, the object appeared to be adjusting its own speed. If true, it would mean 3I/Atlas wasn't behaving like a rock at all. It was acting more like a vessel. Behind closed doors, a handful of senior scientists were said to have briefed the Pentagon and the White House. According to leaked meeting notes from the Aerospace Intelligence Directorate, the discussion revolved around whether to classify the event as a national security anomaly. Some speculated that releasing the full dataset could cause panic. Others believed that silence would only fuel conspiracy theories already spreading online. And they were right. Across Reddit, X, and TikTok, amateur astronomers posted real-time observations showing light fluctuations too precise to be random. Theories multiplied. Was 3I/Atlas a probe? A fragment of alien technology? Or something responding to human observation itself? A small but vocal group of scientists began to question NASA's restraint. Harvard's Avi Loeb went on record with The Hill, stating, "If there's even a 1% chance this object isn't natural, we have an obligation to study it openly." Hiding data doesn't protect anyone, it only delays understanding. Meanwhile, European and Japanese observatories reported similar anomalies but stopped short of public confirmation. All communication between NASA, ESA, and JAXA shifted to encrypted internal channels. For the public, updates dwindled to silence. Then, on the night of October 28th, one day before the projected impact, the Lunar Reconnaissance Orbiter sent back images that defied explanation. They showed a faint oscillating glow trailing behind 3I/Atlas, expanding and contracting as if it were breathing. Within hours, that image disappeared from NASA's servers. When reporters asked why, officials called it a data compression error. But few believed it. As the world stared at the dark side of the moon, waiting for the moment of truth, one question echoed louder than any broadcast. Was NASA watching a falling comet, or covering up something humanity was never meant to see? As the moment of closest approach arrived, the world held its breath. Billions of people looked up at the night sky, searching for a flash, a tremor, anything to prove that what they had feared or hoped was real. For a few endless seconds, the moon hung there in silence, pale and unmoving, as though the universe itself were waiting to decide what came next. No one knew whether they were about to witness a catastrophe or a revelation. Some expected a blinding explosion, others believed they would see nothing at all, that the real impact would unfold quietly in data and memory. And yet, in that collective stillness, something changed. Humanity, for all its instruments and equations, found itself humbled once again before the cosmic unknown. The moon became a mirror, reflecting not just sunlight, but the deepest fear of our species, that we can watch the universe unfold, but never command it. The story of 3I/Atlas was no longer just about science or danger. It was about perspective, about realizing how small and temporary our control truly is. Whether it struck or passed by, the lesson was the same. 3I/Atlas reminded us that the sky we think we know can change in an instant, and that knowledge itself comes at the edge of fear. Perhaps it wasn't destruction the universe was offering, but a warning. Or maybe an invitation to look closer next time. So, what do you think? Was 3I/Atlas a natural test from the cosmos, or something sent here to watch us? Leave your thoughts below and subscribe to MindGap, because what comes next might forever change the way we look at the sky.